This is an initiative by Theories of Everything with Kurt J. Mungle.
Good morning, good evening, good afternoon. Hello to everybody around the world. So, as you may have guessed, this isn't the most professional setup, and obviously I'm not a professional streamer. This is my first video that I'm doing for YouTube. But in response to Kurt J. Mungle, a wonderful science communicator and incredible interviewer who has a lot of different scientists and very qualified people on his channel on a regular basis. Also, you should really check his channel out. It's fantastic. And yes, in response to his contest, I suppose you could call it, this video is my entry, and I doubt it will be as technical or advanced as many of the other entries. Well, I'm going to give it a go. Something that I've noticed in the last few years is that not all of the information that's made available to the public is necessarily accurate. There tends to be a mixture of very qualified individuals who are well studied and well versed in a particular topic, and they are generous enough to provide that information and educate people. And then you have the opposite side of the spectrum, which is people who tend to miscommunicate or to communicate misinformation. That's not to say disinformation. I don't think that they are intentionally propagating information that's not correct. I just think that they don't know any better. And so what I'm going to attempt to do is to build a foundational introduction to modern day physics, philosophy of physics, and everything that we know, everything that we don't know. And it's not about everything I don't know, or this video would take way too long. So let's start with the foundations of modern science. We could go back as far as ancient Egypt if we really wanted to. Historically, they were studying human anatomy, and they they made discoveries that today we would call scientific, but at the time they didn't really know what they were looking at. And we can see with their aerial rituals, they knew what organs were. Well, they knew that organs existed and that everybody had organs, but they didn't know what those organs did, you know. So they might have considered that, you know, your red blood carries your happy emotions and dark blood carries your bad emotions, or whatever. And the point is that they believed in magic, and it wasn't very scientific, and they didn't follow the scientific process as we have it today. They didn't understand experimentation or things of that nature. And then, so you can go a little bit further ahead in history, And you get to the Greeks, Hippocrates, the first doctor, that's where we get the Hippocratic Oath. And they had a scientific method of doing experiments and trying to replicate experiments and results, which I suppose the Egyptians did as well, but as societies progressed, obviously our knowledge base has improved. And so in Greece, you had some of the first medical journals that were really mainstream. Maybe not the first ones, but some of the first. And we had a lot of philosophers, and we had a lot of people asking questions, and we had a lot of people trying to answer questions. And sometimes they were wrong, and sometimes they were right, and sometimes they were half right, and that's not all that different from what we see today. But I'm getting ahead of myself with today. A little bit later on, we got to the likes of Copernicus, Galileo Galilei. We had the likes of Leonardo da Vinci and designing the first flying machines. Maybe not the first, but some of the first flying machines. And so there's a saying that we stand on the shoulders of giants. And I really do believe that that's true, because as one person, you can't discover everything that there is to know. It's thanks to Copernicus that, well, maybe not thanks to Copernicus, but I would go so far as to say if Copernicus hadn't said the Earth is round and we're not the center of the universe, then and if Galileo Galilei hadn't built his first telescope, then Newton's work on, as he called it, the heavenly bodies, may not have progressed as far as it did. Maybe it would have, maybe it wouldn't. I'm not a psychic, I can't tell you. But I think that it's fair to say that Newton's work on the heavenly bodies, and the planets, the stars, the rotation of the Earth, and the path that the Earth travels around the Sun, that built on his predecessors. And so then we came to Einstein, and we came to Niels Bohr, we had Pauli and Dirac. And to some of you, you'll be familiar with these names, and some of you won't. However, I think it's important to mention these people, and also to note that there are many scientists who were never nearly as famous as Heisenberg or Einstein or Marie Curie. Many scientists throughout history have gone unheard of, unknown. Their work and their contributions to physics, chemistry, engineering has been lost to the annals of history. And they just don't have the same publicity or the same fan base, so to speak, that you would find from some of their more famous contemporaries at the time. And that's not to say that those famous scientists should be any less famous. Certainly not. Okay, my microphone wasn't off, so I'm just going to get my editor to fix that. Me being the editor, unfortunately.
Oh, brother, this guy stinks!
Right, so where was I? So, it's not to say that those people should be any less famous. It's just to say that not every great discovery, not every great innovation, not every achievement gets the same recognition as another. And whether that's good or bad or right or wrong, that's really not for me to say. So let's take a moment to really consider the two sides of the spectrum of scientific research. On the one side, we have the ancient draconian way of doing science, which is comparable to the Egyptians or the Greeks or the Romans, where everything had an elaborate story, and it was, we make an observation, and so we assume that, oh, those three stars up there are in a line with each other, and it looks like an archer, so that's connected to some bloke who had a bow and arrow, and maybe he was spirited up by some entity, and we get down to the more nitty gritty of understanding, okay, so if we look at a star through a telescope, we can see what that star looks like, and we can gauge how far away it is using mathematical equations. And then if we look at it through a special machine, we can see what the mass of the star is, or we can see, how far along is it in its life cycle. And that's building on the foundations of science that was laid 100 years ago, 200 years ago. And we found that scientifically, it's very seldom that we find one person who's familiar with every field. We have specialists. And so we may have a nuclear engineer, and they know everything about the periodic table and all of the isotopes, stable, unstable. They understand reactor design and neutron flux and radial and axial emission rates and critical versus supercritical reactions. And then you might ask that person what they think about Schrodinger's cat. Sorry if I pronounced that wrong. I'm not German. Schrodinger. Anyway, his cat. And they might say, oh, well, the cat is dead and alive at the same time. Yet historically, that's not what Schrodinger said. What he said was actually more sarcastic than anything. He was saying that a particle is in two places at once, you might as well say that the cat is dead and alive at the same time, which doesn't work, because if you understand a wave function collapse, you understand that at the moment of a wave function collapse, it means that the probability has now been removed from the equation. It is now a definite. It is determined. It is, for all intents and purposes, it has happened. And so now, in time, it is a definite state. It is no longer a variable. You can reintroduce a wave function mathematically for the purposes of what would have happened, but you can't make it unhappen, because, well, let's look at it like this. Let's say you have a house. Okay. This is my terrible depiction of a house. And inside this house, you have some people, and those people are playing rock, paper, scissors. And this is very oversimplified, but they're playing rock, paper, scissors. And you don't look inside that house. And somebody asks you, well, what's the outcome of that rock, paper, scissors? Well, you can build a matrix operation which describes all of the possible combinations of rock versus paper versus scissors, and you can have 2 rock, 2 paper, 2 scissors, then you can have rock versus scissors, rock versus paper. So you construct a matrix that contains all of those possibilities. And now you do that over multiple games, and you find that the number of possible outcomes grows exponentially. And inside the house, that game of rock, paper, scissors is taking place. It's got the 2 people playing it, they're observing it, that wave function is collapsed inside of the house. It has happened. Now you ask them afterwards, they come out of the house, and you ask, so what were the combinations? And they tell you, oh, well, I played this, he played that, and then this, and then that, and then the next thing. So from a philosophical perspective, you could say that regardless of what the outside observer thinks may have happened, what happened is what happened. And so what necessitates a wave function is not that we have these systems where an electron is in 2 places. The electron is in one place. We don't know where it is until we look. And that's why once you look, the wave function collapses. It's the same as saying, I'm going to play a game of hide and seek, and I'm going to hide, and there's 3 places I could be. Until you find me, there's a probability of 1 in 3. You check 1, it's not there. Now there's a probability of 1 in 2. And if you check the last one and I'm not there, then you know I have to be in the 3rd place, and that's a probability of 1 over 1. It's not spooky. It's not magic. It's necessary, because that's how reality works. So when you have a lot of these videos that are coming out and people are talking about quantum entanglement, quantum superposition, and they're describing the spooky action at a distance, it's horribly, horribly misinformed. And it convinces people of things that simply aren't what we observe in reality. And the worst part is that sometimes you hear it from fairly sophisticated scientific channels where their expertise may be in quantum computing, for example. And so they don't understand what a wave function is, but they know how to assign an operator using a wave function, and they can perform some calculations and do some differentials and build matrix multiplications. And in their mind, they really do believe that there are 2 separate universes in which this is occurring until you observe one, which is just completely nonsense, at least in my opinion. Now, I could be wrong, but then that would mean a lot of respected scientists would also be wrong. So, it's fine. Somebody has to be wrong. But getting back to our points about that rock, paper, scissors chain, I'm not going to draw it out for you as matrix vectors, but effectively, when you're working with probability and you add a new event, you're speculating. So you speculate that, okay, based on its previous trajectory and the density of particles in a given space, you can say that it has a probability of interacting in XYZ way. You take probabilities and you can surmise probable patterns that will come out of that, and that's just what we observe. How we describe it, how we understand it is important, but it's not relevant to the fact that that is what we observe. So we can observe something and not know how to explain it, and then we try to explain it, and then that gets tested, and either it's right or it's wrong, or we simply don't know. But this idea that quantum entanglement is two atoms that are connected physically over theoretically infinite distance is incorrect. How can I say this so certainly? Okay, let me give you a good example. A very good example. And this is, I forget who described it like this the first time, but...
So Einstein, along with two other scientists, Boris Podolsky and Nathan Rosen, EPR for short, came up with what they thought disproved the Copenhagen interpretation.
With the help of two younger colleagues, Boris Podolsky and Nathan Rosen, he formulated another, even more striking thought experiment that shows the non-locality of quantum mechanics. This paper is now known as the EPR paper, after its authors.
Yeah, we have a piece of paper. There's a 1, there's a 2, there's a 1. It would be the other way around, but obviously my camera is mirroring everything. So I tear that apart. Here's 1, here's 2, and I fold this paper. Okay, and I fold the other paper. And now I'm going to randomly mix them up. And thanks to my ADHD, I've got no idea which one has what. So I can't tell you what's in the one, what's in the other, just by looking at these folded up pieces of paper. But I can open one, and very conveniently, it's 1. Could have been 2. So now, using the powers of common sense, I can tell you this one says 2. It can't be anything else. The states are entangled. That is quantum entanglement, except that that's presented on a macro scale, not on a nano scale. So if you have a particle and you stimulate it, let's say you take the photoelectric effect, and you emit 2 electrons from an atom that's being stimulated by photons, which is fairly easy to calculate what the energy emission would be, because E energy is equal to frequency over h bar, which is Planck's constant, and don't ask me to do that for you because it's above my pay grade. But it's easy enough to understand, okay, the more frequently those photons are hitting that atom, the more often it will release electrons. So now you release 2 electrons, okay, and you happen to know the direction that they both went, based on, let's say, an angle. Let's say they're emitted with 20 degrees, roughly, between them. They've got a straight line, and there's 20 degrees. So if you find the one, you can calculate where the other one is at that moment, in that exact moment, because of sine, cosine, or tangent, which is not particularly difficult to do. And so that is quantum entanglement. What we have, quantum entanglement is not spooky action at a distance. Quantum entanglement is the preservation of states. It is the continuity of reality. You slap me today, tomorrow I got slapped yesterday. That is entanglement. It is a continuity. And so we have a lot of these hypothetical, theoretical calculations of wave functions and Hilbert spaces, and we have, there's a 60% chance it's here, 40% chance it's there, so 60% of it is there, 40% of no, that is a formality. It's not a formality. It's just a way of trying to explain something that is probabilistic. It's in one place or the other, but because you don't know, you have to calculate both. That way, if you find it's in a place, you've already done your calculation for it. And then you already have your next part of the equation. You follow along and you find, it's over there. And so now you've filled in the blanks. Because reality is branching. Reality is not a single point in time. It's not a stationary object. Something I like to say is that time is really just a measurement of change in a system, which creates a bit of a paradox, because if you measure change over time, then that would be change over change in a system. But it's actually not that terribly confusing. You see, thanks to the second law of thermodynamics, everything is moving. And it might be that it's moving at an atomic level, or it might be physically moving. But the fact is that there's no such thing as a perfectly stationary object, because either the object is moving and all of its constituents are moving through space, and by moving through space, they are moving through time, or it looks stationary. You have two objects that are stationary relative to each other, but the constituents of that object are anything but stationary. Everything tends towards entropy, a higher level of entropy, which you can define entropy in different ways. You can say entropy is a measure of chaos, entropy is a measure of change, entropy is a measure of whatever you want. But really what entropy says is that energy tends to spread out over time. Not necessarily over T, as in the equation, but over time, energy spreads out. And so you could almost argue that that's tending towards lower entropy if you wanted to. You could argue that it's tending towards a perfect order where the energy is perfectly spaced out and that everything is completely uniform, which would be the opposite of what we define entropy, but that's neither here nor there. When we're looking experimentally, entanglement is not spooky action at a distance. Spooky action at a distance is something completely different from quantum entanglement. Quantum entanglement is the continuity of states.
So we're forced to accept one of two explanations for this experiment. Either non-locality, like the Copenhagen interpretation of quantum mechanics, or a local hidden variable theory. Given that non-local action at a distance contradicts relativity, Einstein thought this was definitive proof that the Copenhagen interpretation of quantum mechanics is wrong, and therefore there must be some local hidden variable theory that will replace it.
You can correlate that if two people walk around the Earth in exactly opposite directions, they will meet up because of geometry and how circles work. If two people go in opposite directions through the universe, well, then they won't meet up because the geometry doesn't allow for it. And so that's a really complicated concept, quantum entanglements, but it can be simplified to understand it in a simple way, because the only way that we're going to have proper innovation from people is if everybody is on the same page, discussing the same fundamental things and referencing the same fundamental things. Maths is important. Maths is a very useful tool, but having a tool that's capable of doing something can have a tool that performs a certain purpose, but at the end of the day, you want to know that the thing that you're building is going to serve its function, it's going to serve its purpose. I can build a machine that peels potatoes, but then it doesn't peel potatoes. I used all the right tools, screwed everything in, but it doesn't peel the potatoes. Well, sorry. You can use the right tools, but if you get the wrong results, it doesn't actually matter. And that's fundamentally where physics is in the modern day, is we have a lot of theoreticians and a lot of experimentalists and a lot of publications, but we have a lot of disagreement over whose work is relevant, whose research is effective. And I would say something is relevant or effective when it has an application that solves a problem, when it performs a function that needs to be performed.
Harvard's Jacob Barandas exposes the hidden assumption that has blinded us for nearly a century. One day, while preparing to teach quantum mechanics, Jacob made a startling discovery. Quantum theory and classical probability are separated by a single, unnoticed presumption, Markovianity. Drop it, and the gap between them vanishes entirely. Even more startling, this mathematical accident bypasses the so-called local realism constraint of Bell's theorem and dissolves the measurement problem, all without magic. This discussion ranges from black holes that rain to the mathematical beauty of indivisible processes, culminating in a meditation on legacy, kindness, and why the next revolution in physics demands philosophers and physicists working as one.
So we've made it through the concepts of what entanglement is. We've made it through what the concepts of superposition is. So why does any of this matter? Why have I been rambling on about what entanglement and superposition mean for the last, in my time, it's probably an hour. Hopefully I've managed to edit this down to 10 minutes. The reason is because quantum entanglement and quantum superposition are arguably the two most important concepts in quantum physics. We can apply field equations and Newtonian mechanics to just about every interaction of every object with mass. And yet, people describe entanglement and superposition as being magic, and they are not magic. You have probability, and you have equations that are designed to work with probability. You have 1 in 5 chance of something, so you have to do 5 equations so that you have the answer ready. Because if you picked one, you might pick the wrong one. It's really that simple. We can get into the metaphysics of how is probability decided and how does the strong nuclear force, the weak nuclear force know how to be random or probabilistic. And the fact is, I don't know. It's outside the scope of my knowledge. It's outside the scope of my expertise. Fundamentally, my expertise lies in computers and not even necessarily the software or the firmware or any of that, more in the hardware. By trade, I don't work in science, but by day I'm just a regular guy. By night, I'm an inventor. And so in order to invent things, you have to know how they work. You have to know why they work. And so perhaps more than anything, that gives me an incentive to understand a lot of a great deal of the technology that's out there. So I've had a lot of theories, hypotheses, ideas in my life. Sometimes they're right, sometimes they're wrong. And I think it's good to try different things, because if you're not trying something, you're not making progress. Sometimes you have to be wrong. And then that gets added to the published literature as incorrect. Then people will look at it and they'll say, that's wrong because X, Y, Z. Well, good. There's a saying in chess that you learn more from one loss than you learn from 100 wins. And I think that's very true in science as well. We can't stick to the established dogma, the established doctrine, and be afraid to experiment with new ideas at the risk of being wrong. Rather be wrong and try something different than be right by repeating the same thing over and over again and always being right. I'm not very good at maths. I struggle with things like linear algebra, differential equations, etc., etc. My maths is really not that great. And so I don't do a lot of calculating, but every so often I can see something from the perspective of a linguistic argument for something. So I might not understand the equations, but once I understand what the equation is trying to explain, then I can say, okay, well, that makes sense, etc., etc. How can we apply this to something in the real world? How can we apply this to something that we experience? And then how can we use that to form a new framework. So just because a person's not fantastic at maths doesn't mean that they can't do chemistry, doesn't mean that they can't do physics or science or philosophy. Maths is important. Maths gives us calculations that prove and disprove things and give us very important answers, but not everyone's good at that. We need people who are experimentalists. We need people who are philosophers. We need people who understand chemistry and the reaction between chemicals, even if they can't necessarily calculate the precise exothermic release of energy from two molar masses and whatever. Doesn't matter. I mean, it matters, but it doesn't matter in the sense that there are people who can do that. There are people that specialize in that. You might have one person who designs machines, another person who builds machines. They work together hand in hand. They're not competing to be better than one another because they are collaborating to be better together, at least in an ideal situation. And so, I think fundamentally some of the most important things that we can hope for in the scientific community is coherence, collaboration, communication, and clear definition of concepts, what things are. You almost have to wonder how many good ideas were overlooked because of a misunderstanding or a misinterpretation of something. How much more progressed would people be if our fundamental framework was more rigorously constructed from clearly defined axioms? And I've tried very hard to use simple language without simplifying the topic. But also because I just don't have as much knowledge as somebody who is highly specialized in any particular field. There are people out there who are far, far better suited to explain complex topics or go very in depth into very intricate and elaborate mathematical equations and how to solve them. And I don't think that it's really all that important that I use this as an opportunity to present all of my ideas and different thoughts and theories. I think that everyone has different thoughts and theories and ideas, and that the difference between success and failure is going to come down to a framework of communication and being able to clearly articulate the causality, the sequence to go from one idea to the next to the next. So one example, one of my interests is photonic computing. And there are many different ways that people can perform photonic computations. Fundamentally, it all comes down to waveguides and emitter and some kind of way to change the emitted beam of photons and a reader, and you can perform matrix operations and some very, very clever calculations using photonics. But we have an issue with storing that information. And so there are many different ideas about how that information can be stored, either electrically or physically, or some people have suggested using a loop. And all of those ideas are relevant, and all of those ideas great, but it's good that people are having ideas. But I think that fundamentally, the most important thing is going to just come down to people's ability to articulate why they think that that idea is going to work. Why do they think that that idea is a good idea? Because they might be right, they might be wrong, but through clearly documenting their reasoning, their thought process, the way that they drew those conclusions, we can learn and apply to more than just the specific field that it's intended for. Personally, I've looked at phase change materials and quantum dots and almost semi-biological structures that can be made from electroactive polymer hydrogels, and so on and so forth, as a means of storing photonic memory, because spectral information just comes down to the wavelength and the frequency, and you can tune that in the form of what we would see as color in the visible light spectrum. But as Tyler False has said, our eyes are really radiation detectors, but just with a very narrow range of emissions that we can detect. But I mean, if you think about that, if you have a means of, changing the color of something, you've got a very, very large range of frequencies that you can represent with that change in color. I mean, it's in the region of terahertz. From, red is a range of frequencies in the terahertz range. And then orange is a range of frequencies. So you have 7 ranges. That's excluding infrared and ultraviolet or gamma or X-ray or other spectrums, which is talking about the ones that we ourselves can physically see with our eyes. There's far more than that, but let's stick to the visible light spectrum because it's easy for us to manipulate. It's easy for us to change. There are many ways that you can store in a physical medium a certain emission range and use that to store information, where you just go back to that medium and shine a light through it, and it gives you the exact frequency it remembers it. It's not going to change. So maybe my ideas aren't the best. Maybe someone else comes out with a better idea. But, I really started on this journey of trying to get back into science by thinking it doesn't matter if I'm wrong, because even if I have an idea that inspires somebody to come up with the right solution, then that's good enough. I don't have to be right. But at the same time, they say even a broken clock is right twice a day. So if you try enough times, eventually you're going to get something right. And maybe it's something nobody's thought of before. So it's good to have an open mind, and it's good to try new things. But at the same time, what's not good is to guess, and to just keep on guessing and guessing and guessing and guessing without having a foundation to build your guesses on. If you take certain axioms that are established, speed of light is a constant, nothing can go faster than the speed of light, and then you build on that, well, maybe you'll be wrong, maybe you'll be right. But if you ask questions like, can a shadow go faster than the speed of light? The answer is immediately no. It's a pointless question. There's no reason to ask that question more than once. Once you've established nothing faster than light, you can start looking into concepts of temporal dimensions, but then you have to have some proof of those things. You have to have some reason why you think it's possible. You have to have an idea that's based on some foundation. Science is hard, science is complicated, and sometimes it's very time consuming and energy consuming, and it can lead you into circles where you're spending years trying to make something make sense. That's part of the journey. But I think that at the end of the day, you have to choose. Do you want to be seen as right? Or do you want to help and further the field? Because if you just want to be seen as being smart, you can tell people, oh, quantum entanglement is spooky action at a distance, and Einstein didn't like it, and Schrodinger's cat is dead and alive at the same time. And that's actually just not what happened. None of that is accurate. None of that is true. It's been debunked by other people who are much smarter than me, much more qualified than me, and historically that's not what was said. And yet we hear it repeated ad nauseum. And every time somebody says it, someone hears it, and that person is now further from understanding what quantum physics is than they were before they never heard that in the first place. Because now you have to undo everything that's right before you can actually correct it. Whereas if a person just had no idea of any of it, you could tell them the right thing and they would know it, and that great. It's like they say, good habits are hard to form, easy to live with. Bad habits, easy to form, hard to live with. And once you have a bad habit, it's a lot harder to turn it into a good habit than it is to just have a good habit the first time around. So this whole treating quantum physics like it's some magical mumbo jumbo that it's mystical and it's metaphysical. It's not. It's really not. One axiom must build on the one that came before. One proof has to build on the proof that came before. And if you have a theory, if you have an idea, if you have some hypothesis, great. Test it, peer review it, see if it works. If it doesn't work, okay. But wrong is wrong. It's just something that you have to accept. Better to realize you're wrong and then do the right thing than spend your whole life trying to make the wrong thing into the right thing, because it's not going to work. Goes north and one person goes south and they're walking at the exact same speed based on their entangled states. You can calculate exactly where it is that they will meet once they reach each other, assuming that, well, obviously once you get to the North Pole, you would be traveling south, and once you get to the South Pole, you'd be traveling north, but assuming you both start at north. Okay, see, that's a prophecy. You can't use that example. Assuming two people start at the North Pole and they both walk in completely opposite directions, they're traveling till they eventually get south. Once they do, you can calculate based on their relative speeds, assuming that two objects.
Stop it. Get some help.